Comets, messengers from the dawn of the solar system. For the first time, we sent a spacecraft to orbit and land on one.
To go outside of the inner solar system and catch a speeding comet, and then send a lander down to land on its surface, that is nuts.
The Rosetta mission answers our most fundamental questions.
Rosetta is really teaching us how comets live in real time. This is a game changer.
Rosetta changes our understanding of the cosmos forever.
The secrets of life itself may be wrapped up on Comet 67P.
"530 million miles from the sun, a tiny lump of ice and rock starts its journey towards the inner solar system."
Scientifically, comets are more precious than pure gold. They are actual time capsules. They are preservations of what the chemistry, the environment was like when our solar system formed. And they hold clues as to how our chemistry arrived here on Earth. Comets are some of the most valuable scientific treasures that exist.
Finding a comet we can study is not an easy task.
Finding the right comet for a mission, it's kind of like you're auditioning them, right? One comes in and it's like, oh, that orbit's okay, but it's not exactly what we're looking for. And oh, this one's too big, this one's too little, this one's too active.
What we really want to see is that comet come from outer parts of the solar system and get heated up as it gets close to the sun, pass around the sun, and head back out to the outer part of the solar system. So you need to get way out in the solar system and catch a comet on its way in.
Comet 67P fits the bill.
The special thing about Comet 67P is how accessible it is here on Earth. It actually orbits around the sun once every 6.5 years. And its orbit doesn't take it all that far out, only about as far out as the planet Jupiter. That gives us many chances to actually reach the comet and successfully rendezvous with it.
Allumage multiple.
67P's moment in the spotlight arrived. The European Space Agency launched the groundbreaking Rosetta probe.
For years, we've studied comets from afar. We had never seen one up close with cutting-edge technology to learn about how comets behave as they orbit the sun.
Missions to large planet-sized objects are hard. The Hubble Space Telescope's blurry images revealed Rosetta's target is just 2 miles wide. And not just a small target, a moving one. Comet 67P races through the solar system at over 33,000 miles an hour.
The precision involved is pretty incredible. It's like making that hole-in-one golf shot from New York to San Francisco.
But catching Comet 67P wasn't just a straight shot.
The spacecraft had to actually get the same sort of velocity as the comet, and with current propulsion systems, we can't achieve that by flying directly to the comet. Instead,
Rosetta performed a slingshot maneuver that would take 10 years.
So what it's doing, it's actually taking some energy away from the planet, so it's slowing the planets down a little bit and then imparting that energy into the probe.
The Mars flyby produced one of Rosetta's most nail-biting moments.
There was one moment that was actually pretty nerve-wracking. The path of our spacecraft had to go behind Mars, into Mars's shadow, as we say, and that means we lost contact with it.
The probe had to go about 250 miles above the surface of Mars. Rosetta is a completely solar-powered probe, so there wasn't enough power to actually keep everything running, so we had to go into a standby mode, so everything was switched off. We weren't 100% sure the spacecraft would turn back on because it wasn't actually designed to do that when the spacecraft was manufactured. That act was nicknamed the €1 billion gamble.
Luckily, the bet paid off. Once safely en route to Jupiter, the Rosetta team could test their instruments as they passed the asteroids Steins and Lutetia.
Neither Steins nor Lutetia had been studied with a spacecraft before, so the opportunity to get up close and to get a picture of their actual surfaces and see the craters on their surfaces was really valuable.
Steins was a small, strange diamond shape,
which suggests either a really bizarre cratering history or some other process that has changed its shape and made it more of a diamond than a sphere or a potato shape.
Lutetia was a miniature world with a diameter of 81 miles.
It might be one of a primordial population of asteroids from the earliest parts of the solar system.
At the time, it was the largest asteroid ever seen in close-up. Rosetta flew past Jupiter, nearly 100 million miles from the warmth of the sun, and entered the most dangerous part of its journey: hibernation.
Even though Rosetta had solar panels on it, it still had to be put to sleep. And the reason for that is that it had to track 67P a ways away from the sun, and there just was not enough collection area and solar power to be able to power the instruments.
It's normal to put spacecraft into hibernation, but the worrying thing at the back of your mind is that it had never been done for this long before.
31 months of hibernation gave Rosetta's team plenty of time to worry about what could go wrong.
It's dark and cold out there in space. There's a lot of things going on. There's a lot of little micrometeorites out there. And without the constant communication with that spacecraft, it just is a little nerve-wracking when the day comes and it's time to flip the switch and turn it back on.
January 20th, 2014. After almost 10 years in space, it was finally time for Rosetta to wake up, reactivate its communication system, and phone home.
I mean, the tension was just palpable. It was just, I mean, how long do we have to wait before we're going to get the signal?
It's got to work. It has to work.
Oh gosh, maybe it's just not going to turn on at all.
Have we lost the spacecraft? And then the peak appeared on the graph. It's like, yes, we've got contact with the spacecraft.
Rosetta began to send back images of its target. And after months of seeing a small dot in the distance, the comet slowly came into focus.
When I saw this comet, crystal clear, this mountain floating in space of ice and rock, my heart just dropped. They are some of the most dramatic, beautiful images I have ever seen.
And then as it got closer and we got to see more and more details on it, yeah, that's when things started getting really strange.
Quite simply, arrival at 67P, we expected to see something shaped like a potato, and we found something shaped like a rubber duck.
67P is no ugly duckling, but its strange shape created a problem for Rosetta. Orbiting the comet was going to be far more difficult than anyone had imagined.
A planet has a lot of gravity, so you can send the spacecraft out there and then just slow it down a little bit with a rocket burn and it'll drop into orbit. In the case of Comet 67P, you're dealing with a very small little rock. The spacecraft cannot feel the gravity of that rock, at least not until it's right up against it.
Well, the engineers had to actually plot triangular orbits. It was a very complicated set of maneuvers.
Once in orbit, Rosetta could start work. Its first task? Figure out how 67P formed.
So how did this comet get this weird shape? There's two main ideas. One is just that it was eroded somehow in the center. And so it started off as a more spherical thing and became the shape it is today through some unknown process.
The other idea is that it started as two separate objects.
Space rocks normally hit each other hard. They collide with an average impact speed of more than 11,000 miles an hour. That's 5 times faster than a rifle bullet. Was 67P involved in a pileup? A clue came from the distinct layers on the comet's surface.
The layers in Comet 67P are a little like the layers in an onion. If you see them aligned, that's a clue that perhaps the object formed as a single entity.
So as far as we can tell, these two separate bodies must have been formed in the same area. They're very similar in composition, but they are so light and fluffy that they would have destroyed each other if they had hit fast.
They had a low-speed collision and basically stuck together like two wet snowballs.
With one mystery solved, Rosetta began to investigate the chemical makeup of 67P. The little comet could answer one of the biggest questions in planetary science. From where did our blue planet get its water? The Rosetta mission, a 4 billion-mile journey to Comet 67P, and a 4.5 billion-year trip back in time to the birth of the solar system.
This comet is a remnant of the formation of the solar system itself. So this is an opportunity to open that time capsule and get a view into the ancient solar system.
Comet 67P could help us answer one of the most important questions about our planet.
One of the big mysteries that we have about Earth is, where did the water come from?
Today, water covers over 2/3 of the Earth's surface. But it wasn't always that way. 4.6 billion years ago, the inner solar system formed from a maelstrom of rocky debris. Temperatures were so hot, any water on the early Earth boiled away.
What the evidence suggests to us is that Earth's water arrived at Earth after the Earth formed. And the primary mechanism that we thought were responsible were comets.
You have to remember that comets are basically just big balls of ice and dirt. One of the main goals of the Rosetta mission was to analyze the water on this comet and see if it matched the water on Earth.
Comets come from two regions at the outermost reaches of our solar system: the Oort cloud and the Kuiper belt.
The Kuiper belt is in the plane of our solar system, and the member that most people are aware of is Pluto. But beyond that, there is a spherical distribution of icy bodies, the Oort cloud.
This is a repository of comets that extend for hundreds of thousands of times further away from the sun than we find the Earth. And it's kind of a big spherical cloud around the sun that's a kind of deep freeze for a bunch of big comets.
Billions of icy objects orbit safely beyond the chaos of the inner solar system, locking in primordial water.
The lifespan of a comet is fascinating. They might do absolutely nothing out there for over 4 billion years until the right tweak of their orbit or tug from a planet changes everything. And all of a sudden they're on a path in towards the sun, and that ice that's been in deep freeze for billions of years starts to heat up.
Astronomers believe that Comet 67P's former home turf was the Kuiper belt, until something sent it ricocheting inwards.
The influence of the gravity of Jupiter, because Jupiter's such a massive planet, it actually attracted the comet and pulled it into the inner solar system.
It slowly was perturbed and migrated into the inner solar system where we see it today. It's traveled, I mean, not just billions of miles in linear space, but I mean, really, when you think of all the orbits it must have made, just trillions upon trillions of miles, that's quite a journey for such a little object.
Now, 67P loops around the sun in a 6.5-year orbit that travels as far out as Jupiter and closer in than Mars. As it gets nearer to the sun, its frozen ice begins to heat up, leading to a famous effect: the comet's tail.
Sunlight comes in and heats up the comet's surface, and it gets transferred to the interior where there's a lot of ice, and the ice gets heated up and it vaporizes and makes its way to the surface. And once it's sitting on the surface, the solar wind is bombarding that comet, and it drags all of that material out into a long, beautiful tail.
Rosetta flew into the tail to analyze the water vapor. Its goal? Confirm it's the same type of water as we have on Earth.
Water does come in different flavors. And I don't mean salt water or fresh water. I mean what the water's made of, its molecules.
We're talking about the actual chemical makeup on the proton, neutron, and electron level. So you might have heard of heavy water before, and that just means that there is an extra neutron.
It's H2O, but one of the hydrogens has an extra neutron. So we call it deuterium. And so that water actually weighs more than normal water because of that extra neutron in the mix.
On Earth, there are roughly 160 molecules of heavy water for every million molecules of normal water. As Rosetta moved around the comet, it measured the ratio of hydrogen to deuterium in the water vapor. An exact match to Earth's ratio would confirm that comets were the source of our oceans. But Rosetta discovered something surprising.
What Rosetta found was that the deuterium to hydrogen ratio was 3 times that of the water in Earth's ocean. That means a comet like 67P couldn't have been the source of Earth's water.
If it was the same as the measurement of the ocean water, then we could have said that these comets could have been a delivery mechanism for the water that we see on Earth. The fact it was 3 times higher kind of indicates that comets like 67P were not the source of the water that we see on Earth today.
But although comets like 67P didn't deliver our water, we can't rule out all comets.
We have to keep this in perspective. 67P is but one comet. And what we know about objects like comets is that they come in families, and these families have different compositions. So it could be that some have Earth-like water, and those are the ones that brought water to Earth, and some don't.
I don't see wrinkles like this as going back to the drawing board. Sure, we get more questions sometimes than answers, but that allows us to probe farther and really expand our knowledge into how planets formed.
Rosetta's mission to Comet 67P planned to answer the biggest questions in planetary science. And none is bigger than figuring out the origins of life on Earth.
Life on Earth got started not long after our planet cooled, something like 4.5 billion years ago. But we don't know the exact process. Did all that stuff come together here from molecules on Earth and become more and more complex? Or was it brought from space?
Rosetta began to hunt for the building blocks of life, basic organic compounds.
So we always thought that comets probably carried organic materials, but we really couldn't confirm that until Rosetta.
It detected aliphatic compounds, which are organics rich in carbon and hydrogen. And that is the first time such a substance has been detected at the surface of a comet.
These materials are the raw building blocks for making things like proteins, which are required for all life. And this is really important because this says that possibly these materials were delivered to Earth by comets.
The idea that comets carry the building blocks for life across the solar system is known as molecular panspermia.
You can kind of think of comets as being like space delivery trucks, right? They're forming out there in deep space. All this stuff is being formed with them, and then they bring it to Earth. Now, you don't want your delivery truck smashing through your front door, but in the case of comets, when they impact the Earth, they can distribute those molecules all over the place.
But in some way, we're kind of skipping a step, right? I mean, so the comet may be bringing the ingredients of life to the Earth, but where'd the comet get those ingredients?
The answer may be in deep space, in the matter and radiation floating between star systems in a galaxy. It's called the interstellar medium.
The really interesting result is that the overall composition of Comet 67P and some of the really interesting ingredients in that comet are very similar, identical in some cases, to materials we find out there in the interstellar medium, floating out there in the gas and dust between the stars.
If this organic chemistry is common on Earth, it's likely to be common across the entire galaxy. this chemical kit for making life is universal, and therefore perhaps life itself is common. There could be plenty of wet rocks out there in the night sky teeming with life, with this universal chemistry kit.
But scientists still couldn't figure out the origin of one vital element.
So phosphorus is one of the atoms is absolutely essential for life, but we don't really know where it comes from.
Phosphorus is a vital part of DNA, cell membranes, and energy production.
But the problem is it's quite scarce in the universe, and it's certainly scarce on the surface of the Earth. Any phosphor that was around would have been locked up in the soluble rock, so that wouldn't have been available for life to use at that time.
If rocks had locked in all the mineralized phosphorus, where did the phosphorus needed for biological processes come from? 67P held the key to the mystery.
What we found on the comet is bioavailable forms of phosphorus, not just mineralized phosphorus.
Bioavailable phosphorus is a form that life can use. But where did Comet 67P get it from? In January 2020, astronomers combined data from the Rosetta mission with ALMA's observations of the star-forming region AFGL 5142.
AFGL 5142 is a stellar nursery, a gas cloud where large and small stars are being born simultaneously. And it's very close to us, which means we can study it in great detail.
The ALMA Observatory takes really high-resolution images of different types of dust and gas in very, very close to a star that's just formed. So you can actually see the process of formation happening.
The largest stars live fast and die young, exploding in supernovas.
So the phosphorus itself, we believe, is formed in massive stars. So essentially, it's created as the star gets to the end of its life, and when the star goes supernova, it spews this phosphorus out into the interstellar medium.
When mid-sized stars burst into life, they sent shock waves and radiation through the cloud, transforming phosphorus into a form biology can use: phosphorus monoxide.
The phosphorus monoxide can freeze out and get trapped on the icy dust grains that remain around the star. These dust grains can come together to form pebbles, rocks, and eventually comets that become the transporters of phosphorus monoxide.
Scientists trace the cosmic trail of phosphorus and organics from stars to comets to planets and even to life.
You could, in theory at least, take the sort of chemistry you find preserved in a comet and use it to construct a cell.
So often people seem to think of astronomy as the study of things that are very far away, that have absolutely no bearing on our day-to-day life. Nothing is farther from the truth. We are looking for the origins of ourselves out there, and we are discovering them. So a basic question like, how did phosphorus end up in our DNA, when the only place you seem to find it is in around young stars, clouds, thousands of light years away? Now we know the mechanism because we asked the question, and now we understand ourselves that much better.
The next stage of the mission was to get the lander onto the comet's surface. But there was a problem. The craft's landing gear was broken. Would the team have to abort the mission? Rosetta had discovered the building blocks for life on 67P. Now the probe faced its toughest challenge so far: a historic first landing on the surface of a comet.
One of the biggest challenges about setting the Philae lander down on the surface is having no idea what the surface is like when you're designing the lander. Is it going to be like rock or ice and be very stiff? Is it going to be brittle?
Philae had harpoons to dig into the soft surfaces and top thrusters to stop it from bouncing off the comet. The lander team discovered neither system was working properly. With the odds stacked against them, they decided to go for a landing anyway. Philae made a slow 12-mile, 7-hour descent. Until finally, touchdown.
So when we got the first signal of touchdown, we were relieved. The lander was down and everything was good to go. But then we realized things weren't quite going to plan.
The data from the lander was intermittent. The only possible explanation? It was tumbling end over end.
It could have bounced and bounced right off the comet and continued all the way into space.
We really didn't know. We just knew we were not on the ground and we were rotating and tumbling.
Then, 12 minutes later, a ray of hope.
We saw a flash on one of the computers and we huddled around it and we realized that the lander was actually sending data back as it was programmed to do. We were actually doing science on the comet and getting the results back.
The lander stopped tumbling. Philae's solar panels weren't fully operational, and the tiny craft's battery had only 60 hours of power left. It was a race against time.
We had to completely rip up all of our plans of what we wanted to do, and then we had to rewrite everything to maximize the amount of science return in those 60 hours we had available to us.
Philae got to work. Its first discovery: the ground was stranger than expected.
One of the things we found about the surface is the top 40 centimeters were a very fluffy material.
It's not dense and rocky, it's pretty fluffy. You could imagine something on the order of cigar ash. Imagine the rocks on Comet 67P, but imagine them being as light and fluffy as cigar ash.
It's so crumbly that if you had it in your hands, you could break it apart with almost no effort at all. It has a fraction of the strength of styrofoam.
Philae's bounce landing helped investigate the surface.
By bouncing, we actually were able to sample 2 sites, and interestingly, both sites were different. That kind of shows us that the comet is not homogeneous, it's not all the same material.
Philae's instruments revealed Comet 67P is not just 2 lobes fused together. The comet formed from distinct blocks pulled together by gravity. Philae's onboard camera also fed back vital clues to the lander's final resting place.
The images taken by the lander were really amazing because from those we were actually able to work out Philae was on its side.
Philae's location was unknown, far from the planned landing site. With its battery dead, it couldn't speak to Rosetta.
The problem with not knowing exactly where on the surface of the comet we were was that some of the instruments had needed to know that exact location to actually interpret the data, and without that information, the results were meaningless.
Time is passing and still no Philae lander is to be found. Is there hope? Is all lost?
When you make or follow a space robot, you kind of get invested in that success and the survival of that robot. You want it to succeed against the harsh reality of space. You feel like you've lost a pioneer, you've lost a fellow explorer.
After 7 months of hibernation, Philae woke up and spoke with mission control. A fleeting call from a lost lander.
We got very excited because we knew it was waking up, it was charging up, it was seeing sunlight, and it was doing everything it was supposed to do.
But the calls faded away, and in March 2016, the little lander was declared lost.
Declaring Philae lost was a very, very sad moment because it was almost like losing one of the team, and at that stage, the lander element of the mission was over, and as was our role in the mission.
As Rosetta scanned the comet, searching for the lost lander, it faced a new problem.
As this dirty snowball races towards the sun, the radiation from the sun heats it up, and so it starts snapping and popping and cracking, transforming itself. It's like a fireworks show.
Huge jets blasted material from the surface. Would the outbursts launch Philae into space? Rosetta's lander, Philae, was lost somewhere on the surface of Comet 67P, its battery dead and its solar panels useless. As Rosetta scanned the comet for the missing probe, it flew less than 2 miles above the surface, close enough to cast a shadow.
Seeing the shadow of the spacecraft itself on the comet really brought home the fact that there was a piece of humanity, one of our machines, right there. It makes the hair on the back of my neck stand up. It gives me chills.
The low passes allowed Rosetta to smell the comet's surface.
The Rosina instruments allowed us to actually measure the chemicals and the gases coming off the comet, so we can actually put those together to make a comet perfume. So what we've actually done is impregnated those smells of the comet into a card, a bit like a scratch and sniff card, so you can actually smell, and that is the smell of the comet.
And it's not very pleasant. If you can imagine a mixture of something like rotten eggs and cat urine and like bitter almond stuff, it's not something I would want to have to be able to smell.
To me, it kind of smells like baby's nappies, and it's a bit of a pungent, quite an unpleasant smell.
Months passed with no sign of Philae.
The comet isn't terribly big, where could it be hidden? And if we understood where it was hidden, we would understand the images that it had returned so much better. There was sort of that human part of like, where is my buddy? And also that science part of what was it trying to tell us?
Then, an eagle-eyed researcher spotted something in the corner of an image.
The lander itself was a tiny little speck, and you really have to zoom in to actually see it. But there was Philae, under a cliff.
Seeing a little Philae lander there, on its side, under a ledge, in the shadows, was just remarkable.
Pinpointing Philae's location on the smaller lobe solved one final mystery. It explained data sent back months earlier, revealing this area of the comet is solid.
There was a real sense of closure, and there was sort of a Godspeed to it, like, we know what's happened to you, thank you for the science. And that was its final resting place, and it was really wonderful to see.
Philae was an amazing success. Despite all those problems, we got the lander down. Despite the bounce and it coming to a rest under the cliff face, we got actually amazing images and some fantastic measurements of the gases and the structure of the comet itself, which we would never have had we not tried to put a lander on a comet.
Rosetta's mission was not over. As the comet approached the sun, chaos erupted.
All of a sudden, there were these jets that would appear and eject a huge amount of material from the interior.
When sunlight warms the comet's surface, ice turns directly into gas. The uneven surface of the comet funnels the escaping water vapor into narrow jets of gas and dust. But Rosetta also spotted huge, violent gas outbursts.
We would expect to see jets on comets that kind of gradually rise and fall with the solar illumination, but these outbursts were utterly different. They would just sharply increase and then stop.
These outbursts weren't timed with the sun. They came out at random times, so there must be something else going on.
The outbursts exploded in sudden, brief, high-speed events.
Because we only take pictures of the surface every 5 to 30 minutes, when we see an outburst in only one image, we know that the whole event lasted less than that time, which is very mysterious.
So it was like putting together a puzzle, and you have 1,000 pieces and you're putting them together and you realize, oh, I only actually have 600 of the 1,000 pieces and I've got to make sense of this, and it's really frustrating.
As the comet swung closer to the sun, Rosetta's cameras captured 34 outbursts in just 3 months. They were all huge.
In the span of only a few minutes, a single jet can release up to 260 tons of material. And one jet was spotted releasing 40 pounds of material every single second.
The cause of the outburst was a complete mystery. Then, in September 2014, close-up images revealed a 230-foot-long, 3-foot-wide fracture on the cliff edge named Aswan. Less than a year later, Rosetta photographed a large outburst from the same region of the comet. When the probe investigated the area, it found a devastated landscape. The cliff had collapsed in a huge landslide.
This is like a crime scene. We have the before pictures and the after pictures, and we have to solve the mystery of how this happened.
What links the outburst and the cliff collapse?
We think there's a domino effect going on here, where the sun heats up some of the volatiles deep under the surface, and they sublimate and turn into a gas, and they find any little crack or crevice they can to shoot out of the comet. But that process weakens part of the comet's face.
This is going to release more material, and as it does that, it's going to start forcing gas up through kind of nozzle-like features, having them act like jets. And as they do that, then that's going to cause even more weakening of the material and maybe a large-scale collapse, which could actually cause a giant outburst.
We think escaping gas weakens the surface, which triggers a collapse and a release of gas in a giant outburst.
Like sticking dynamite charges in the side of the cliff and then setting them all off.
Comet 67P revealed the hidden geological activity going on inside these dirty snowballs. And Rosetta spotted another surprising phenomenon. Strange shapes moving across the surface. Dunes.
Dunes aren't driven by wind. Well, on an airless comet, how do you have that happen?
Rosetta rewrote the book on how comets form, how they live, and how to explore them. When Rosetta flew close to the surface, it spotted something unexpected. Dunes.
These are serious dunes. They're about 6 feet high, and they extend for hundreds of feet in every direction. So we've got to figure out what this mechanism is that it's causing this, pretty significant geologic structure on the comet.
Janie Radebop is a planetary scientist. She studies space dunes on Earth.
One of the most fascinating things that Rosetta saw on 67P was a set of dune-like features on an airless body. These were found up by the neck region in a set of soft sediments, and they actually looked very similar to these ripple-like landforms. They were spaced about 10 yards across, and there were maybe 10 to 15 of them across the surface, and we even saw them change over time. When we first saw these, no one had any idea what could have formed them. In fact, people even doubted that they were dune-like landforms, because how would they possibly form on a body that has no atmosphere, let alone any wind?
On Earth, land heated unequally creates winds.
The atmosphere on Earth and the really transient atmosphere on a comet are very different from each other. On Earth, it's a stable, thick, dense atmosphere. It's got constant solar heating that can pick up air masses and move them across the surface and generate wind.
Comet 67P does have an atmosphere created when the sun heats the surface, releasing gases. But this atmosphere has a maximum pressure 100,000 times lower than Earth's. Using Rosetta images, researchers in France modeled the movement of gases on the surface of the comet. And they think they've found the answer.
Researchers found that there are winds on the comet's surface. These are brief, and they form because gases escape on the sunlit side, and then they rush over to the cold side across the surface, and this movement of air across the surface is what picks up the sand and forms the dunes.
The grains on the comet are far bigger than sand grains on Earth.
On the Earth, the sand dunes are made of grains about this size, but on the comet, the sand dune grains are this size. Gravity also plays a really important role in moving grains around on the comet. The comet has such a low density that if you were walking around, you'd be able to fly into orbit very easily. And so a grain this big but low density would easily be lofted by the very thin air there.
After 2 years orbiting the Sun with Comet 67P, Rosetta's mission was almost over.
So the plan was to lower the orbiter down towards the surface in a controlled way. And this would allow very high resolution images to be taken and also to get some gas measurements right close to the surface of the comet.
September 30th, 2016. Rosetta spent 14 hours slowly free-falling towards the comet, taking photos on the way down.
As Rosetta was lowered, it touched the surface, and then the link back to Earth was broken, and the mission was effectively over.
The thing that's kind of wonderful about it is that there's a little piece of us on that comet out there right now. As that comet spins around out to Jupiter and back every 6.5 years, it will always have a little bit of humanity on it.
There was one final twist to Rosetta's story.
We thought we had the last image back from Rosetta before the planned end of the mission. But it turns out that actually just before touching down, before the comms were able to finish transmitting back to Earth, an incomplete packet of information was sent back.
The computer discarded this incomplete data packet. Recently, human experts re-examined it. The result? Rosetta's closest photo of 67P.
And the image is amazing because when you actually blow it up and look at it, you can actually feel like you could reach out and touch the surface.
It's a fitting postscript to the only mission to land on a comet.
It's an incredible chance to learn about the geologic structure at the size scale of a human being exploring there. It's a way to look at comets that we've never had before.
The Rosetta mission has transformed our understanding of comets.
Between the strange shape and the measurements of heavy water, we're finding that there's a big diversity out there of comets, and that every time we go to visit a new one, we're probably going to be surprised all over again.
Rosetta may inspire new missions.
We may actually be returning to Comet 67P itself. There's a lot more there to discover about the origin of our lives, ourselves, here on Earth.
There's so much more to learn and so many more mysteries to uncover.